Hello and welcome once again to the Aakash BYJU'S YouTube channel. My name is Atiullah and I'm back with a live session on JEE Mission 2022. How have you guys been? So good to be back. So I see guys joining in already. So before we begin our session, as usual, just let me know if you can see me properly and you can hear me clearly so that we can proceed with this session. Okay, give me a thumbs up, give me a yes, and we're going to quickly start this very awesome session. Alright, so we have people joining in. Sanju is saying, hi sir, you are doing a very good job. Thank you so much Sanju for your kind words. Ramiz, Musharraf, Dilkash, Om, good evening, very good evening. Hello guys, so good to join you here. Swastika is already here. Good evening, very good evening. So I think quickly give me a thumbs up and yes, so that you know that so that I know that I can you guys can see and hear me clearly. Okay, and then we'll quickly start our session. Yes sir, would you going through from basics? So Utsav, obviously we are going to discuss all the concepts. So the difficulty level of questions can be from very easy to difficult as well. Okay, so I'm going to cover everything. Alright, awesome guys. Good to have you here. Very good to be back doing this session after a little bit of gap. So this session we have chosen for atoms and X-rays. Okay, atoms and X-rays. Modern physics in general is very neglected, okay, but I say that this is your golden ticket to your JEE exam. Okay, you can skip if at all there comes a situation where you can either study rotational motion or you can study modern physics. I'll say skip rotational motion, but you cannot neglect modern physics. It's your ticket. Okay, it's a difference between getting selected and not getting selected. It is a difference between getting an average rank versus a very good rank. Okay, so we are going to talk about atoms and X-rays, Bohr's model. We're going to discuss all of that so that we do a quick revision of the topic and never forget that. Okay, you need to do this chapter very well. Sitter, very easy questions. You can solve all of them. Okay, so you already know the format. We're going to solve all the questions together, and if you have any confusion, anything you want to know from me regarding this session, just go ahead and ask. Alright, so let's get started with this session, and here is the first question for you. Where's the question? Alright, here's the question. Okay, let's start. A small particle, let me choose my pen. Okay, alright, 1 second guys, where are we? Yeah, we're here. So what is the question? A small particle of mass m moves in such a way that the potential energy of the particle is given by half m square omega square r square, where omega is a constant and r is the distance of the particle from the origin. Assuming Bohr's model of quantization of angular momentum and circular orbits, show that the radius of the nth allowed orbit is proportional to root n. Okay, that is the question. And before we begin our discussion, I want to know from you what is the concept involved, what is the key concept involved over here. Okay, we are talking about potential energy, we are talking about Bohr's model, we are talking about the quantization rule of angular momentum, we are talking about circular orbits, we are talking about a lot of these things. But I want to know from you what is the core of this concept. Okay, what is the key concept involved in this question. Okay, Gorathnath, very good evening. I thought I think you want to say Sirji, but you have written Sister Ji, so that's fine. Okay, Astha, are we doing questions? Yes, Astha, we are doing questions, but along with the questions, we are also revising all the concepts. Okay, so it will be a combination of both. Right guys, so from you I want to understand first what is the key concept involved, and then only we are going to go and talk about solution of the question. Okay, the purpose of all these sessions is to revise the concepts, be absolutely clear with the concepts. Okay, so what is it? Okay, so Riddhi is saying Bohr's postulate. Right, Bohr's postulate. So what are those Bohr postulate? What is that very important Bohr's postulate that we have to apply over here? Alright, let's talk about it. Okay, first of all we have potential energy. Okay, Now these things, this particle, okay, it is going in a circle, okay, it is going in a circular orbit. This particle is going in a circular orbit, so it is undergoing circular motion. So if it is undergoing circular motion, then there has to be a centripetal force. How can we figure out what is the centripetal force? And Sayyam has shown that, has commented about that. Yes, Swaraj is also right. So if we have to find out what is the force, and we have been given potential energy, so the conservative force associated with this potential energy will be equal to minus du by dr, okay, and that force will be the centripetal force in this case, and that should be equal to what? That should be equal to mv square by r. Is that correct? That is the first concept that is applied over here. The second concept applied over here is the quantization of angular momentum, okay. The angular momentum of this particle about the center, it is quantized, that it can only follow nh by 2 pi. It will be an integral multiple of h by 2 pi. Is that correct? So these are the two things that we'll have to consider, and then we can solve this question. Alright, so let's quickly solve this question. Yes, Riddhi is absolutely right. Perfect. Swastika is asking, energy is not radiated. That is the problem of Bohr's model. So if Bohr's model says that the accelerated charge particle does not lose energy, it's not true. It's true, but they do not provide a explanation for that, and that is the problem in this model. But we have to assume that energy is not lost, energy is not radiated, the particle is not going to release any energy. That we'll have to consider. Okay, now if we do minus du by dr, what are we going to get? This is minus sign, this is u. So this is going to become half into m square, omega square is a constant. The differential of r square is going to be 2r. So force is going to come out to be omega square, m square omega square into r. Okay, I'm not taking care of the negative sign, because negative sign simply means it's an attractive force. So this force is going to be towards the center. So this is the centripetal force, and this centripetal force has to be equal to mv square upon r. Is that correct? Okay, so what do we get over here? We get so this m and this m will be gone, and then we'll have m omega square r square is equal to v square. Okay, and so what we have over here is that v is equal to, what is v is equal to? V is equal to under root of m into omega r. Okay, so what we have figured out is the relationship between v and r. Is that correct? Okay, now this is the first thing that we have done. The second thing is we have to use the concept of quantization of angular momentum of circular orbits, which means the angular momentum, okay, we have skipped too far. The angular momentum, why are we skipping two slides at once? Hang on. Okay, probably we missed this. Okay, now the angular momentum, what will be the angular momentum of this particle? So it has a speed of v and the radius of the orbit is r. So the angular momentum would be mvr, and this is going to be equal to nh upon 2 pi. Is that correct? Okay, and we have already figured out from our calculation that v is equal to root m omega r. V is equal to root m omega r. So what we can do over here is we can do the substitution of v. So let's do the substitution. So this becomes m, and then we'll have root m omega r square is equal to nh upon 2 pi, and then what do we have? We have r square is equal to n h upon 2 pi, then we have omega, then we have m to the power 3 by 2. Now you can see that all of these things are constants. So r square is proportional to n, so r is going to be proportional to n to the power half, and that is going to be our answer. Is that right? Yes, absolutely guys, you are absolutely right. So these are the concepts involved in this question. Now listen to this very carefully. Now in Bohr's model, what force is providing the centripetal force? The electrostatic force is providing the centripetal force. Okay, so when we derive all the things for Bohr's model, when we derive all these quantities for Bohr's model, so these are the only two things we take care of. What is the first thing? The first thing is the centripetal force. The centripetal force is going to be mv square by r. Now in different systems, your centripetal force can be different. For example, the centripetal force in this particular question had a different nature. The centripetal force in Bohr's model will have a different nature. The centripetal force in some other setting will have a different nature, but that does not matter. The only thing is that we have to find out what is the centripetal force, and that will be equal to mv square by r, and the second equation is going to come from the quantization of angular momentum. mvr is equal to nh by 2 pi. So you can be given different settings, but in all those settings, the way to find the relationship between velocity, radius, energy, everything, the way to find that is by these two equations, centripetal force equation and quantization of angular momentum. Is that right? All right. Okay, so Nitesh is saying, sir, I did not understand that part. Which part are you talking about, Nitesh? Let me know. I can explain that to you. Not a problem at all. Just let me know which part was unclear. Okay, so it is important to remember all the results of Bohr's model. What is the result for, what is the expression for the radius, what is the expression for energy, what is the expression for velocity, all these things we have to remember, yes, but we also have to remember and understand the derivation, okay, because they can use the same principles but put it in a different setting, just how they did in this question. Is that correct? All right, so I hope that is clear, and with that said, let's proceed to the next problem. Now find the radius of Li2 plus ion in the ground state assuming Bohr's model to be valid. Okay, it's a very simple question. All I want to do is revise the results. So we know that R is equal to A naught into N square divided by Z. Is that correct? Do you remember this? The allowed Bohr orbits, the allowed radius of the Bohr orbit is given by A naught into N square divided by Z. Do you remember that? Okay, and what is A naught? A naught is 0.53 angstrom, or you can also say it is 53 picometer. Is that correct? Okay, so from here what do we have? We have Li2 plus. So remember, Bohr's model is only valid for isoelectronic species. Okay, now Li has 3 electrons. Li2 plus ion has only 1 electron. So we can apply Bohr's model for Li2 plus. Remember, this is very important, that Bohr's model can only be applied to ISO 1 electronic species. Okay, so let's do that. Now all we have to do is simple application of this result. Okay, what is A naught? A naught is 53 picometer. And then N square, what is N? N is the nth orbit. We are talking about the ground state. If we are talking about the ground state, what is N? N is going to be equal to 1. So 1 square divided by Z. What is Z? Z is the atomic number of this atom. And lithium, the atomic number is 3. So if you calculate this, this is approximately going to come out to be 18 picometer. Is that correct? Okay, so Muhammad is asking, I think Muhammad is asking related to the previous question. He is asking, its rotational kinetic energy was completed some times ago. So I think it's rotational. Why would we include the rotational kinetic energy? Number one, it is going around the center. Okay, it's not that it is rotating about its axis. It's a point particle. It is just going in circular motion. But we don't have to find the kinetic energy. If we had to find the kinetic energy, we could have used half mv square. That's absolutely right. We calculated V. So from there we could have calculated its kinetic energy. But that's not required in the question. What is required in the question is the relationship between R and N. That is why we took two equations. One, the equation for centripetal force, and number two, the quantization of angular momentum. Is that correct? Okay, so I hope I have answered your question. All right. Perfect. So this question that we are currently dealing with is a very straightforward question, but my objective was to revise the result. Okay, so I hope this is clear. So now we are going to go to the next question. Okay, now let's talk about, now we are talking about the kinetic energy. Okay, Now, the kinetic energy of an electron in the second Bohr orbit of a hydrogen atom is, that's what we have to find out. And A naught is Bohr's radius. What does it mean? What is Bohr's radius? Can you tell me what is Bohr's radius? So Bohr's radius is, what is A naught? A naught is basically the radius of the ground state of hydrogen atom. A naught is radius of ground state of hydrogen atom. So we have to find out the kinetic energy in terms of A naught, and these are our options A, B, C and D. And before we attempt, I want to know from you, how do you think we should proceed? Okay, first I want to understand from you what is the process we should follow to solve this question. Any hints, any suggestions are welcome. Yes, Sayam is saying 0.529 angstrom. That is absolutely right, but we can approximate that to 0.53 angstrom as well. And we can write it as 53 picometer as well. That's all acceptable. Alright, so guys, regarding this question, I am open to suggestion from you guys. How should we proceed with this question? Okay, first I want to know your suggestions, your thinking about this. We have to find out what is the kinetic energy of the electron and some information regarding which orbit, second Bohr orbit, and then what atom is this? This is hydrogen atom. So they have given us N, they have also given us what is Z. They have given us which orbit and we have also specified what is N. Alright, let's think about this. Work energy theorem. Alright. Sayam, can you elaborate on that? Why are you talking about work energy theorem over here? Pratham is saying, sir, it's good to see you again. Thank you so much, Pratham. Yes, it's good to see you guys back. Really excited about that. Now let's get to this question. What is the question and how do we proceed with it? Okay. Now this is Bohr's orbit. This is Bohr's. So kinetic energy we know is given by half mv square. So if we are able to find Alright, so sorry guys, my camera got turned off. Yeah, so my camera was not taking power supply, although it was connected to the power supply, but it was not doing that. It got turned off, so sorry about that. But we are back. Okay, don't worry, we are back. And chalo, let's get back to this question quickly, not waste any more time. So the kinetic energy is given by half mv square. Okay, so our objective is to find v. Is that correct? So we can use the Bohr's model to find out what is v. The other way to do it is that we can also write it as k is equal to p square upon 2m, where p is the linear momentum. Do you agree? We can do that as well. And why I am doing this is because we can use Bohr's quantization rule. And how do we use Bohr's quantization rule? mvr is equal to nh by 2 pi. Do you agree? mvr is equal to nh by 2 pi. And here mv is already there, right? So mv term is already there. So from there we can directly find out what is the linear momentum, and from there we can directly find out what is the kinetic energy. Is that correct? Okay. Now we have to find out what is r. R is a naught into n square divided by z. Do you agree? Now in this question we are talking about the second Bohr orbit, which means n is equal to 2, and the hydrogen atom, which means z is equal to 1. So this is going to become a naught into 4 divided by 1. Now we can do the substitution. So now let's quickly do the substitution. So mv is going to become p, and p into r is 4a naught. This is going to become nh upon 2 pi, and what is n? N here is 2, it is given in the question. So 2h upon 2 pi. Is that correct? Okay. So this 2 and this 2 is gone, and from here we get p is equal to h upon 4 pi a naught. And from here finding kinetic energy is very straightforward. Kinetic energy is going to be p square upon 2m. So this is going to become h square upon, we'll have 16 pi square a naught square, and then we'll have 2m, which means our final answer is going to be h square divided by 32 pi square a naught square into m, and that should be our answer. Is that correct? Alright, so now let's have a look at the options. If we look at the options, we don't have an option. Oh, we do have an option. Okay, so option C is going to be our right answer. Is that clear? Okay, any problem here? So all we are practicing here is the results that we have been using in Bohr's model. Alright, easy questions so far, but my objective is to revise all the concepts for you. Alright, so now let's go to the next question. Now calculate the wavelength of radiation emitted when helium plus makes a transition from the state n is equal to 3 to the state n is equal to 2. Okay, very simple question. We have to find out what is the wavelength of the radiation emitted in case of helium plus. Okay, electron is making a transition in helium plus from n is equal to 3 to n is equal to 2. Alright, so before we proceed with this question, I want to know from you, what should we do over here? What is the key concept involved? Okay, can you recall that? Can you quickly recall that and let me know? What is the key concept involved? Let's think about that. Alright, so there are two ways of doing this question, and you can decide which one is the one you want to follow, but I'm going to show both the ways to do it. Okay, the first is the Rydberg formula. What is the Rydberg formula? The Rydberg formula is 1 by lambda is the wavelength of the radiation emitted is equal to rz square into 1 upon ni square minus nf square. Do you recall this? What is R? R is the Rydberg constant. R is called the Rydberg constant. What is the value of the Rydberg constant? It is 1.097 into 10 to the power 7 per meter. Is that right? Okay, so we can directly use this equation. So let's use this equation. So this is going to become 1 by lambda is equal to r. We can approximate it to 1.1 into 10 to the power 7. We can approximate it to that. And then we have Z square. So what are we talking about? We are talking about the helium ion. What is the atomic number of helium? The atomic number of helium is 2. So 2 square and then 1 upon Ni square. Okay, n from n is equal to 3 to n is equal to 2. So what is Ni square? Ni square is going to be 1 upon 9, or I think it should be the opposite. It should be Nf square minus Ni square. Okay, that should be the transition. So Nf square is how much? Nf square is 2 square and then Ni square is going to be 3 square. Okay, so that is going to be our calculation. So 1 by lambda is going to be equal to 1.1 into 10 to the power 7 into 4, and then we have 5 divided by 9 into 4. So this 4 and this 4 is gone. So lambda is going to come out to be how much? Lambda is going to come out to be 9 upon 5.5 into 10 to the power 7. Is that correct? Any problem over here? Okay, we are simply using the Rydberg's formula. That's all we are doing. Okay, now this calculation that can be done very easily. It's a very straightforward calculation, and when you do this calculation, you are going to get lambda approximately equal to 164 nanometer. I'm skipping the calculation in the interest of time. Okay, so that is how we can do it. But there's another way which we can do it, and if we use that method, my understanding or my intuition says that your calculation is going to become easier, your solution is going to become easier, and this is going to help you in many other questions. Okay, it is going to help you in many other questions. Okay, let's try understand what to do over here. So we know the energy of the hydrogen atom. Okay, we'll take the hydrogen atom energy as reference. So we know the energy of the hydrogen atom for various states. Okay, we know this already. For n is equal to 1, this is minus 13.6 electron volt. For n is equal to 2, it is minus 3.4 electron volt. And how are we getting this energy? We are getting this energy from this relationship. E is equal to minus Z square upon n square into 13.6 electron volt. Is that correct? Now if you put Z is equal to 1, which is corresponding to hydrogen, and then keep dividing it by n square, then we'll get the energy of the different states for the hydrogen atom. Okay, and if we do that, for n is equal to 3, we are going to get minus 1.5 electron volt. For n is equal to 4, we are going to get 0.85 electron volt, negative obviously. And for n is equal to 5, we are going to get minus 0.55 electron volt. Now my suggestion to you would be to remember this value. Okay, I know it might be a little tedious to remember, you may forget, but my suggestion to you would be that if you remember these values, it is going to make your calculation very simple. Okay, let's see how. Now E is equal to minus Z square upon n square into 13.6 electron volt. Is that correct? Okay, so what we are going to do is we are going to find the difference in the energy of transition. Okay, we are going to find the difference in the energy of transition. So can I say this is going to be equal to Z square? So I'm saying that the energy of transition of any atom other than hydrogen, any atom, is going to be equal to Z square into the energy of transition for the hydrogen atom. Okay, so if you isolate Z square from here, the rest of the term is the energy of the hydrogen atom. Okay, so if we take a delta difference on both sides, this is what we are going to get. Is that correct? So finding the energy of transition for any atom is very simple. Okay, so this transition is happening from n is equal to 3 to n is equal to 2, from this energy to this energy. So can we find the energy of transition? This is going to be equal to Z square, and we are talking about helium. So this is going to become 2 square, which is 4, multiplied by the energy of transition for hydrogen atom. Same transition for hydrogen atom. It is going to go from minus 1.5 electron volt to minus 3.4 electron volt. And how much is that going to be? That is going to be 1.9 electron volt. Is that correct? Okay, so energy of transition you have very easily calculated. Clear? Okay, now once you have calculated the energy of transition, then lambda is very simple. Lambda is going to be hc divided by the energy of transition. Okay, So Hc, we know the value of Hc as 1240 electron volt nanometer, and then we have to divide it by 4 into 1.9 electron volt. Is that correct? So electron volt and electron volt will be gone, and the answer you are going to get is in nanometer directly. Okay, so according to me, this is a faster way of solving the question if you remember these values, and it is going to help you in other questions as well. So my strong suggestion to you would be to remember these values for hydrogen atom, and if you know these values for hydrogen atom, you can find it for any atom in which Bohr's model is applicable. Is that right? Is that clear? And if you do the calculation, obviously you are going to get the same result, approximately equal to 163 nanometer. Is that clear? Okay, Hyper Gaming is saying, sir, simple formula based question है. Correct. ये जो पूरा बोर्स मॉडल है ना, पूरा मॉडर्न फिजिक्स है ना, ये फॉर्मूला बेस्ड ही है. ठीक है. There are concepts, obviously there are concepts, but the application of those concepts is very simple. वही, for example, if we take atoms and X-rays, ठीक है, वही 3-4 फॉर्मूला में पूरी दुनिया इसकी खत्म हो जाती है. And that is what I'm trying to emphasize here, कि इतना सिंपल है कि छोड़ना नहीं है. Okay, so basics revise कर लेना है, सारे questions, सारे results हमें देख लेने हैं, and then trust me, you will be able to solve all the questions. Okay, even in JEE, the level of questions is going to be very straightforward. Okay, not to worry at all. All right, so we are done with this. All right, now let's go to the next problem. Okay, are you guys ready for the next problem? All right, so find the wavelength of the radiation required to excite the electron in lithium 2 plus from the first to the third Bohr orbit. Clear? Is the question clear? How many spectral lines, that's the second part of the question, how many spectral lines are observed in the emission spectrum of the above excited system? Okay, is the question clear? If the question is clear, I want to know from you, how should we proceed? Okay, what is the concept that is involved? Okay, what is the key concept involved? We're going to discuss that, and then we're going to go to the solution of the problem. Alright, so Anaira is saying, sir, I'm a NEET dropper, but is it going to help if I watch this lecture? Absolutely, Anaira. Be it JEE, be it NEET, it is going to be very helpful. Okay, modern physics is almost the same level in both JEE and NEET. So yes, definitely, it is going to help you. Pratham is saying, sir, EMI is my favorite topic in physics. Mera bhi, same pinch. Even my favorite, one of my very favorite topics in physics is EMI, electromagnetic induction. Beautiful, beautiful topic. Very interesting. Okay, and very scoring also, be it from a JEE standpoint also, that is very, very interesting. Alright, perfect. Now let's get back to this question. Pratham is saying Rydberg equation. Yes, we can certainly use the Rydberg equation, or as I said, if we can know the energy of transition. Okay, so what were the energies? So the transition is happening from the first to the third Bohr orbit. Okay, now this is very simple. If it is going from the third to the first orbit, then photon is going to be released. But if the photon of same energy is going to go and provide the energy to the atom, then the electron is going to transition from n is equal to 1 to n is equal to 3. Okay, so it's the same thing. So the wavelength of radiation would be the same when the atom is going to come down from n is equal to 3 to n is equal to 1. That's it. Okay, so for the hydrogen atom, okay, what are the energies? For the hydrogen atom, what are the energies? Can you quickly, do you remember it? So minus 13.6 electron volt, and then we have minus 3.4 electron volt, and then we have minus 1.5 electron volt, and so on. Okay, so we are talking about the transition from 3 to 1 or 1 to 3. Okay, so what will be the energy of transition? The energy of transition is going to be Z square into the energy of transition of the hydrogen atom. Is that correct? So what is Z over here? We have lithium, so Z is going to be 3 square, which is 9, And what will be the energy of transition? So it is going from minus 13.6 to minus 1.5. What is the energy of transition? The energy of transition is 12.1 electron volt. Is that correct? So we have very quickly found out what is delta E. So lambda is going to be Hc upon delta E. Okay, and what is Hc? Hc is 1240 electron volt nanometer approximately. That we are going to divide by 9 into 12.1 electron volt. So as you can see, electron volt gone. And if you calculate this, you are going to get your answer in nanometer. Is that correct? Okay. Any problem? Yes, hypergaming, absolutely, it's good to remember all these values. Okay, it's very important to remember these values. Trust me, it is going to save some time for you. Alright, so if we do this calculation, I'm sorry, I'm skipping the calculation in the interest of time. It's very straightforward, simple calculation, nothing much. So lambda is going to come out to be approximately 11.4 nanometer. Okay, but there is another part to this question. How many spectral lines are observed in the emission spectrum? Okay, let's talk about that. So let's say this is n is equal to 1, this is n is equal to 2, and this is n equal to 3. Okay, now transition can happen in both ways. Okay, so if the transition, if the atom is absorbing energy, then it will be in the absorption spectrum, and if the atom is releasing energy, then it will come in the emission spectrum. Okay, but let's say it is the transition is happening from 3 to 1. So how many ways are there to go from 3 to 1? One is that you can directly go from 3 to 1. The other is that you go from 3 to 2, and then you go from 2 to 1. In all these cases, the energy of transition is different, and if the energy of transition is different, then your wavelength that is going to be emitted through that spectrum is also going to be different. Is that correct? So how many possible scenarios are there? The possible scenarios are 3. There are 3 possible scenarios in this case. So what will be my answer? The number of spectral lines is going to be 3 corresponding to 3 wavelengths. Is that correct? Now this is also a general question. Now if we had n equal to 4, if the transition was happening from n is equal to 4 to n is equal to 1, then there will be still more possibilities. Okay, the more spaced these energy levels are, more would be the number of possibilities. So I am going to generalize this. So the number of spectral lines observed will be equal to NC2. Think about it. So the transition is happening between any 2 energy levels. Okay, how many energy levels are possible? N. Let's say it is going from n to the ground state. Okay, so how many energy levels are possible? N energy levels are possible. If we can choose any 2 energy levels, then the transition can happen between those 2 energy levels. So in how many ways can we choose 2 energy levels out of n energy levels? NC2. Okay, so NC2 is going to give you a general solution. So you can remember this. Is that correct? Alright, so I hope this is clear and you are able to follow the concepts. Again, my emphasis is to revise the concepts and the results. Okay, it is going to help you revise much more effectively and in a shorter duration of time. Alright guys, any problem up till here? I hope everything is clear. So now let's go to the next problem. Okay, and now we are talking about X-rays. So again, X-ray is a very neglected topic, but there are just 2 or 3 concepts in X-rays. That's it. If you are able to do those concepts, then you should be able to solve questions on X-ray. Very simple questions. You should not leave it. At least 1 or 2 question can come on X-ray. So it's 3 marks for, 3 or 4 marks, whatever be the pattern, for no effort at all. Okay, very little effort. Okay, so let's do this. Now an X-ray tube is operated at 20 kilovolt and the current through the tube is 0.5 milliampere. Find the number of electrons hitting the target per second. That's the first part of the question. The second part of the question is the energy falling on the target per second as the kinetic energy of the electrons. That's the question. Okay, so take some time to absorb the question and tell me how should we proceed. Okay, how many of you guys have studied X-rays? And how many of you guys have absolutely neglected X-rays? You can put that in the chat box. So my recommendation would be that don't leave X-ray, and we are going to do 2 or 3 questions on X-ray, and that is going to be enough for you to understand what is X-ray about. Okay, you can always go back and do more questions, but in these 2-3 questions the concepts are going to get revised. Okay, now let's look at this. Now the operating voltage of the tube is 20 kilovolt and the current is 0.5 milliampere. Okay, what is current? The current is charge upon time. Okay, so let's say this is the tube, and through these tubes electrons are flowing. Okay, now the current is equal to charge divided by time. Okay, what are these? These are electrons. Okay, these are electrons. Electrons are flowing. So electron will have charge equal to the electronic charge. So we can say that if there are n electrons, then the charge is going to be n into E. So that is the total charge flowing. And if it is flowing in t time, then the current is going to be the charge divided by time. So current is Ne divided by t. Correct? But what is asked in the question? What is asked in the question is n by t, the number of electrons which are passing per unit time. Is that correct? That is what is asked in the question. The number of electrons hitting the target per second. Per unit time, what is the number of electrons hitting per second? So what we need in this question is n upon t. So n upon t is equal to I upon E. So all we have to do is find out what is I upon E. So what is I? I is 0.5 milliampere. So 0.5 into 10 to the power minus 3 ampere divided by E, which is 1.6 into 10 to the power minus 19 coulomb. Is that correct? Okay, so we can do this calculation. This is going to become what? This is going to become 5 upon 16, and then we'll have 10 to the power 16. Then this is going to be 50 upon 16 into 10 to the power 15. So 2 8 times and then 2 25 times. So this is going to be something like 3.1 into 10 to the power 5 electrons per second. Okay, that is going to be my answer. Alright, so Dhruv is saying not done, sir. Hypergaming is saying not done, sir. It's not done, man. You should absolutely do X-rays. Okay, trust me, it is going to take half an hour to 1 hour, and that is going to gift you 3 or 4 marks in your question in your exam. Okay, so you should absolutely do it. Okay, and when we are doing these questions over here, then also you'll understand a little bit of X-rays. So that is also going to help. Okay, so the first part of the question we have calculated. The second is the the energy falling on the target per second as the kinetic energy of the electrons. Okay, so how is X-ray produced? When energetic electrons are accelerated and they fall on a metal target. So we have to find out what is the amount of energy falling per unit time as the kinetic energy of the electrons. Okay. So these are electrons. Let's say this is the metal target. If it is accelerated through a potential difference of V and the electronic charge is E, then what is the kinetic energy? The kinetic energy is going to become EV. Is that correct? Is that clear? Okay. So if it is accelerated through a charge E is accelerated through a voltage V, then the kinetic energy is going to be E into V. Okay, and what we need is kinetic energy per unit time. Is that correct? What we need here is the kinetic energy per unit time. Okay, so if we divide this by time, then what do we get? We get EV upon T. Clear? But if we go back a little bit, we have found out this relationship. So from here, can I say that E by T is going to be equal to I upon N? Do you agree? E by T is going to be equal to I upon N. So I can substitute that over there. So this is going to be equal to I upon N into V. So that's what we have to find out. So what is I? I is 0.5 milliampere. So 0.5 into 10 to the power minus 3 ampere divided by N. Okay, what is N? Did we calculate N? I think we had calculated N. Let me go back. I'm sorry. slight mistake over here, so we had taken the energy of only one electron. That's my mistake, I'm sorry about that. So let's say there are n electrons, so this is going to be Ne, so this is going to be n into eV. Okay, so the energy of one electron is going to be eV, but let's say there are n electrons, so the kinetic energy is going to be n into eV. Now if we divide it by T, then we are going to get the kinetic energy per unit time, and then this quantity we can get from the previous equation. Okay, and how much was this? This was the current. So this is going to become the current into the voltage. Okay, simple calculation here. This is going to become current. The current is 0.5 into 10 to the power minus 3 ampere multiplied by the voltage. The voltage is 20 kilovolt. So 20 into 10 to the power 3 volt. Is that correct? So 10 to the power minus 3 and 10 to the power 3 is gone. So we are going to be left with 10 joule per second. So the amount of energy falling per second on the metal target is 10 joule per second. Is that clear? So we have done both the parts A and B. So far, this is the use of 20 kilovolt. This is the use of 20 kilovolt that we have just done. Okay, we found out what is kinetic energy per unit time. It came out to be I into V. Because of that potential difference, the electron is getting accelerated, and that acceleration is causing its kinetic energy to increase. That is the point over here. Alright, now let's get to the next part of the problem. What is the next part of the problem? We have to find out what is the cutoff wavelength of the X-ray emitted. Okay. Now how is continuous X-ray emitted? Can anyone let me know? How is continuous X-ray emitted? When electrons, highly energetic electrons, are falling on the metal target, they can have an energy between 0 and eV. Do you agree? Okay, they can have an energy between 0 and, they'll have an energy EV. They're accelerated, they will have an energy EV, but what fraction of that energy they are imparting to the metal? Okay, what fraction of that energy they are imparting to the metal? If they are imparting them no energy, then the energy loss is going to be 0, and if they are imparting their entire energy, then the energy loss is going to be EV. Is that correct? So the energy imparted by these accelerating electrons to the metal can be something between 0 and EV. Okay, and depending on what energy they have lost, that will dictate the wavelength of the X-ray emitted. Okay, that will depend on the energy of the photon of X-ray that is emitted. Is that correct? Okay, so lambda is going to be hc divided by delta E. I should write it delta E. What is the energy imparted? So lambda is going to be hc upon delta E. Now if it is able to impart a high amount of energy, then the wavelength is going to be small, and that is called the cutoff wavelength. Okay, so if in the case when it is able to give all of its energy, okay, which means that entire energy EV it is able to provide, then in that case the wavelength is going to be minimum. Is that correct? Okay, so lambda is going to be, or I can say lambda cutoff is going to be equal to hc upon delta E. Is that correct? Okay, and that is the mechanism of the production of continuous X-rays. So hc is 1240 electron volt nanometer, and then divided by delta E. What is delta E? The maximum value of delta E can be E into V. So it is going to be E into, what do we have? We have 20 into 10 to the power 3 volt. Is that correct? Okay, so this becomes electron volt, and this, by getting multiplied, one electronic charge into volt is going to become 1 electron volt. So we are left with 1240 upon 20 into 10 to the power 3. Is that correct? Okay, so this 0 and this 0, so this becomes 62, and this is going to give us 0.062 nanometer, and that is going to be our answer. Is that clear? Okay, so while doing the question, we have also understood the mechanism of the production of continuous X-rays, and we have also seen what is the cutoff wavelength, right? So I hope that is clear, and now we get to the next question. Alright, what is the next question? Now the figure shows the intensity wavelength relationship of X-rays coming from two different Coolidge tubes. Okay, two different Coolidge tubes, two different experiments, which means two different metals, and the graph is coming from the data of those two. The solid curve represents the relation for the tube A, in which the potential difference between the target and the filament is VA. Is that clear? And the atomic number of the target material is ZA. So it has been accelerated by VA in tube A, and the atomic number of the metal is ZA. And for the same quantities for the other one, the dashed graph, it is VB and ZB. Now we have to find out a relationship between VA and VB and the relationship between Zn and ZB. That is the question. Okay, read the question carefully and quickly let me know how should we proceed with this question. Hyper Gaming is asking, cutoff wavelength means somewhat like threshold. Yes. So this is basically the cutoff wavelength. This is the graph of intensity versus wavelength. So you can see that from here up till going forward, okay, you can have many wavelengths. You will have different wavelengths of different intensities, but you don't have any wavelength below this. Okay, so this is called the cutoff wavelengths. So in the X-ray that is emitted, in the X-ray which is radiated, you will not get any wavelength below this value. That is why it is called the cutoff wavelength. Alright, let's think about this. Let's think about this. So what we see over here is the cutoff wavelength of A is less than the cutoff wavelength of B. So I'm talking about lambda. So lambda here I mean is the cutoff wavelength. So cutoff wavelength of lambda is less than the cutoff wavelength of B. And what does the cutoff wavelength depend upon? It depends upon Hc upon delta E, which is Hc upon EV. Is that correct? So higher the accelerating voltage, lower is going to be the cutoff wavelength. Okay. So lambda A is less than lambda B, which means we can say that VB is going to be, or VA is going to be greater than VB. Is that correct? So VA is going to be greater than VB, which means either of options A or B is going to be correct, but we also have to look at ZA and ZB. Is that correct? Okay. Now my next question to you is, how is characteristic X-rays formed? Okay. In characteristic X-rays what happens? So you have a nucleus and then you have these electrons around the nucleus. Okay. So what happens? There is an electron. So these accelerated electrons, they come and they eject an electron from a shell completely. They knock it off. So when they knock it off, there is a vacancy created, and the electron from any other level can come and basically fill that vacancy. Is that correct? Okay. So in that case, the wavelength of the X-ray is Hc divided by the energy of transition. Is that correct? That is going to be Hc divided by the energy of transition. So what we see over here is, for same K alpha, okay, for same K alpha, which means the energy is filled from L shell to K shell. Okay, the electron has transitioned from the L shell to the K shell. That is K alpha X-ray. Now, so for same K alpha X-ray, the wavelength is lower for B and the wavelength is higher for A. Okay, so we can see here is that lambda B is less than lambda A. Do you agree? This is the wavelength of the characteristic X-ray K alpha. Is that correct? Alright, so lambda B is less than lambda A, which means the energy of transition of B is going to be greater than the energy of transition of A. Do you agree? Think about this. If lambda B is less than lambda A, it means that the energy of transition of B is going to be greater than the energy of transition of A. Do you agree? So energy of transition of B is going to be greater than the energy of transition of A. And what is energy of transition? Now if this charge, if the atomic number is higher, the charge is going to be higher and this electron is going to be more attracted. And if you want to detach it, you have to provide more energy. Okay. So for the atom, for the metal for which the atomic number is higher, the energy of transition is also going to be higher because more energy is required to knock this off. Do you agree? Is that correct? Okay. So what we can see from here is that ZB is going to be greater than ZA. Okay. So that is what we have found out. And then if we look at the options, then we'll have option B as our correct option. VA is going to be greater than VB and ZA is going to be less than ZA is going to be less than ZB. Okay. So doing these questions itself, we have understood what is characteristic X-rays, what is continuous X-rays, what is cutoff wavelength, etc. Okay. So one more concept I want to deal with very quickly. Within 5 minutes I want to deal with this concept, and that is Moseley's equation. Okay. Now Moseley's equation is given by this. Root nu, what is root nu? Nu is the frequency of the X-ray emitted, frequency of the characteristic X-ray emitted. Okay. So root nu is equal to A into Z minus B. A and B are constants and Z is the atomic number. So what is the question? We have to find the constants A and B. And what is the data given? That for molybdenum as the element, Z is 42 and the X wavelength is 71 picometer, and for cobalt the atomic number is 27 and the wavelength of K alpha X-ray is 178.5 picometer. Okay, so we have to find out what is the constants A and B. Okay, so we have to remember Moseley's law. Okay, they can be a very straightforward direct question on Moseley's law. So it is given in the question that this is frequency, but the data is provided in terms of wavelength. Not a problem at all. We can convert frequency to wavelength. So we can say that C upon lambda 1. Okay, for frequency I am substituting C upon lambda, and lambda 1 means I am talking about molybdenum. So C upon lambda 1 is equal to A into Z1 minus B, and what is Z1? Z1 is 42. And then if I write the same thing for cobalt, we'll have under root of C upon lambda 2 is equal to A into Z2 minus B. Okay. Now what are the things which are known? We know what is the speed of light C, we know that. We know what is lambda 1, we know what is lambda 2, we know what is Z1, we know what is Z2. What we don't know is A and B. Is that correct? Okay, so we have two equations, two variables, we can solve this pretty easily. Okay, if we divide the equations, we are going to get under root of lambda 2 upon lambda 1, and that is going to be equal to Z1 minus B upon Z2 minus B, and from here we can calculate B, and then we can substitute it in any other equation and find out what is the value of A. Is that right? Okay, so if we do this calculation, I am skipping the calculation part, then we'll have the values of A and B like this. I hope you'll be able to do this calculation. You can note this down, the answers, and you can solve it later as well. Alright, so that is it about Moseley's law. Alright guys, so I hope this session was helpful for you. So this is the end of the session. I hope this was helpful for you, and what I want to emphasize on very strongly is that you should not miss a single topic of modern physics. Okay, it's not going to take much time, very simple topics, and you're going to do them in very short amount of time, and it's going to be super helpful. Okay, so with that said, I'm going to meet you very soon in the next session. I'm going to see you tomorrow. Tune in tomorrow at 7 o'clock, and we're going to solve previous year questions on atoms and X-rays. Okay, so that is it for this session. See you very soon, and thanks a lot for watching.